In the previous video, I went over the derivative for a general polynomial. There are various other functions, though. One of the other types of functions that we're concerned about are basically harmonic functions or periodic functions, like sine or cosine. Those can represent periodic phenomena in a way that a normal polynomial really can't do very well. So I think it's also important to show how the concept of a derivative can be applied to those functions. So in this video, I'm going to try to derive the derivative of the sine function and also the cosine function if I have time. So we're just using the normal definition of the derivative here, as you can see, but we want to find some way to simplify it in order to progress. So if you look at this for a bit and you know your trig identities, particularly your uh, angle addition formulas, an idea might jump out of you. If you we there's a way that we can rewrite this term right here. So we can actually use the following formula, and this is a plus b equals sine a cosine b plus cosine a sine b. So this is a special formula that we can use, and I'm actually going to plug this in. So a is t, and b is going to be delta t. So let me plug that in and see what we get here. So sine of t cosine of delta t plus cosine of t sine of delta t. And then all of that over, or actually, I almost forgot, sine of t over here. And then all of that over delta t. Limit as delta t approaches 0. So this is what we add, and is there any way we can rearrange? So one thing that we see is that this term here has a sine of t in it, and so does this. So we can actually group these two together and kind of reverse distribute the sign, basically pull the sign out. So we can actually represent that as sine of t cosine delta t minus 1. Okay. And then times cosine of t sine delta t all over delta t. And obviously the limit still. Okay, so what can we do now? Well, one thing to notice is that we actually do sort of have a separation here. So we basically have sine of t, which isn't dependent on delta t at all, actually. This term here is not dependent on it. This is really a constant with respect to the delta t. So in the same story over here. So what we could actually do is we could apply the limit to each term, and this is using a special limit property that I haven't gone over, but it's basically a known property of limits. The basic idea is that you have if you have, if you're trying to find limit of as x approaches 0 for f of x times g of x, that's the same as, you can basically apply the limit to each product. A limit of products is the same as a product of limits, basically, for certain assumptions. So limit of x of f of x, that'll be a certain number, and you can just multiply that, or basically just multiply that by the same thing for the other function that's a product. So this is the product property for limits, or the product rule for limits, as opposed to the product rule for derivatives that we might talk about later. And we also have basically the sum rule. It's basically the same thing. It's just sum instead of product. So, whoops, let me do that. So 0 f of x plus g of x is the same thing as limit of x approaches 0 f of x, which is some number. It's basically sort of that you can regroup them. That's all. Those are the only real properties that we're going to invoke at this step, at least. G of x. So just keep these properties in mind. I'm not going to prove these. These are proved elsewhere, and they're somewhat involved. They're actually sort of difficult to understand. You really wouldn't be expected to prove this at a normal calculus course, so I'm just going to forget about it as well. So anyway, as we write this here, we have limit of delta t approaches 0. Actually, I'm going to factor out the sine as well, because the limit of the sine function is just going to be sine. There's no delta t here to plug in, actually. So I'm just going to represent it this way. So sine of t times the limit of delta t as delta t approaches 0 of cosine delta t minus 1 over delta t. So that's that. And then I'm going to kind of do the same thing on the other side. So cosine of t times the limit as delta t approaches 0 of sine delta t over delta t. So if we step back, we can see that the answer is basically assuming that these limits approach some numbers, which again, we really haven't shown, but assuming they do, this is actually some linear combination of sines and cosines. Now, I'm not going to go into the proof of why these exist, or of actually what these limits are. I'm just going to say that this one is equal to 1, and this one is equal to 0. So, again, I'm not going to prove that. I actually have a video here on Khan Academy that I think does a really good proof, in case you're interested in this sort of thing. So I'm actually going to make a link here. So that's actually a really good video to look into, if you're concerned about this. And I'll post this in the description. Yeah, I'll post this in the description for this video. But this is basically the limit of sine x as x approaches sine of x over x as x approaches 0. The variable doesn't matter, so that's the same thing for delta t as it approaches 0. That this video here, it basically gives you a nice geometric argument for why this is equal to 1. So, and similarly, if you know that this is equal to 1, I can actually I'm gonna hold off on that. Basically, if you believe the geometry on this, which this video proves, then this limit equals 1, and the fact that this limit is 1 implies that this limit is 0. So that I'm just going to leave it at that right now. But obviously, if you accept that, so I'm sort of asking you to accept it on blind, on faith here. But if you do accept it, then what that implies is that the derivative is just cosine. So when you hear in your calculus class that the derivative of sine is cosine, this is why. And now I want to also sort of do the derivative of cosine just to get an idea of that. And remember, this relies on basic trig identities. So we basically just use this angle sum formula. Sorry about that. This angle sum formula right here to expand this. And we're gonna do the same thing with sine in a minute here. But if you basically, or sorry, the same thing with cosine. But if you do this, it basically, and you break it down to these limits, assuming that you can verify these limits, which you can, then this logic is actually solid. So I'm just gonna leave that there. So the next one, let's try to see what cosine of t. Take the derivative of that, see what that is. That's just gonna be limit of delta t is limit as delta t approaches 0 of cosine t plus delta t, just the standard definition, minus cosine of t all over delta t. And we're going to use a similar formula here. The formula is actually a little different with cosine. So the formula is cosine of a plus b equals cosine a cosine b minus sine a sine b. So that's the formula that we're going to use now to represent this. So I'm just going to rewrite it here. Just limit delta t approaches 0. And we're going to say t is going to be a and delta t is going to be b in this case. So we're going to say cosine of t cosine delta t minus sine of t times sine of delta t. Or, whoops, delta t. And then we're going to subtract cosine of t from that. And we're going to divide everything by delta t. So just trying to rearrange here. If you look at, we have the cosine t term, cosine t here. So we're going to try to do a similar thing that we did last time around. And just basically see how we can simplify things and reduce the limits as much as possible. So we have cosine t cosine delta t minus 1. And then we have here, we have minus sine of t sine of delta t all over delta t. And we're just going to use the same kind of product. If we look at the product and sum rules from before, so basically for limits at least, the product and sum rules for limits, that you can basically distribute limits into products or sums of various functions. Then that would apply the following. That would apply, we're talking about cosine of t, limit delta t as it limit as delta t approaches 0 of cosine delta t minus 1 over delta t, and we have minus sine of t times the limit delta t approaches 0 of sine delta t over delta t. So same story as before. Almost running out of room there. So actually I can shift this over, I think. There we go. That's better. So that's, whoops, shouldn't do that. There, just leave it there. That's good enough. So if you look here, so we have the sine of delta t over delta t. Well, that's familiar. We look up here, and actually not, up here, and we saw that this equaled 1. So this, remember, this is the same thing. It's really a convenient fact of the angle sum identities that these following limits pop out for both sine and cosine, and that's actually what provided the motivation to actually figure out what they are. So the way that this is figured out is basically with a geometric argument, and then once you know this limit, if you actually try to calculate this limit, you can basically use the fact that you know this limit to find this one out. So it's actually kind of a convenient fact that works out the way it does. But anyway, the limit of this sine of delta t over delta t is 1. So, let's replace that with 1. This is 1, and remember this other one here is 0. So, cosine times 0 minus sine times 1 is equal to negative sine. The derivative of cosine is equal to negative sine t. And this is what you'll find in a normal calculus class. You can actually derive all the other ones like tangent, secant, cosecant, cotangent, but you need to know some other rules in calculus. One of which is called the product rule, and one of which is called the chain rule. You might also use the quotient rule, but the quotient rule is really a special case of the chain rule. But anyway, I hope you got an idea of how the basic thing to keep in mind here is that sine and cosine are basically the derivatives of one another. So if we graph this, so let's say that's pi, and let's make this pi over 4, pi over 2, pi, or 3 pi over 4, and 2 pi, and we'll make that 1, negative 1, and we basically want to graph sine and cosine. So obviously sine is 1 there, and it's or sorry, I drew that wrong. That's my bad. Do this instead. So that's my fault. Let's just do it over pi over 2 increments. So how about that? And there. Now that should be correct. So we know that sine is equal to 1 here, 0 here, negative 1 here. 0 here. And if you're not familiar with this, you might want to review your sine and cosine unit circle. Unit circles kind of the main concept that's used after a trig class. So this one here is sine of let's call it sine of t. And then the cosine, if you remember, that's 1 here at 0. Remember, this is 0 right here. So that's 0, or it's 0 there. It's negative 1 at pi there, and it's back up at 1 here. So we go here. The key thing to keep in mind is it almost looks like cosine is sort of lagging behind sine, which it is. It's basically lagging by pi over 2 degrees, or yeah, pi over 2 radians, I should say. So this one is cosine. But if you think about it, what's the derivative? The derivative is showing how fast something is changing. So if we look at, say, let's look at sine at pi over 2. So the tangent here, remember in previous videos we talked about how the tangent is sort of the same idea as the speed or the derivative. Here you have here's the sine function. So at pi over 2, the slope of this tangent line is 0, which corresponds exactly to the cosine being 0. At here, it's basically, I don't know what the exact slope is, but it's basically, or actually, I'm sorry, I do. It's if you look at this slope here, it sort of looks like -1. I didn't draw it perfectly, but it looks like -1, and that's the actual value of cosine here, -1. If you look at sine, or if you look at, or sorry, this is the sine here. Here we go. It's 0 again. So the tangent of this line is 0, and I actually didn't draw this very well, but the value of cosine is 0. See, the value of cosine always corresponds to the slope of the tangent line of sine. That's the key takeaway, and that's actually the definition of the derivative. So here you think the value is 1, and the value of the slope is 1 here, and the value of the function of cosine is 1 here. So no matter where we are, the slope of sine equals value of cosine. This is actually what it means to be the derivative. Now, I'm not going to go and show you that the derivative of cosine is negative sine, but I think you can sort of get an idea. If we took this sine function and we flipped it around, similar logic would hold in the opposite direction. So these actually do have a physical meaning, and it's actually very interesting because basically it means that if you take the derivative of a sine function, you'll get a cosine function. If you take the derivative of any trig function, they can be represented as other trig functions, which sort of makes sense, I guess. But anyway, that's just a very interesting property.